Hey everybody, it's Coach Stoltenberg again. This is going to be part 3 of your thermochemistry notes video. Today we're specifically focusing on specific heat and doing the calculations for it. We'll also talk about something called calorimetry, which is basically the experimental study of specific heat. But it doesn't. The calculations we'll be doing will be using the same equation. All right, so let's get into it. Just another basic algebraic equation here. We have 4 variables. Actually, one of them is not technically not a variable. Specific heat is a known factor for most substances at this point. But you will have problems where you'll be solving for specific heat. All right, well, let's look at some of these. These are all kind of look a little different. Some will be familiar, some not at all. All right, so CP, that's this symbol. That's what the symbol we'll use to represent the specific heat. If you're given it, that's where the specific heat goes. If that's where you're solving it, that's where your unknown is. The second equation over here is just an algebraic manipulation of the first. I usually just write this one every time. I don't. If you want to use this one, it's fine. I mean, it's the same equation, but I usually just write the numbers out like this. All right, so CP, that's specific heat. Q is heat lost or gained. Q is the energy that's going to be lost or gained. Q will either be in joules or kilojoules, sometimes calories, but most of the time we keep it in joules. Lost or gained is a real important aspect here. Whether you're losing energy or whether you're gaining energy affects the value of this number. A loss of energy means a negative Q. A gain of energy means a positive Q. So if your Q ends up being a negative number, that means energy is being lost or given or given out. And if it's a positive number, that means energy is being input. Negative Q, exothermic. Positive Q, endothermic. Okay, delta T, this little triangle we've talked about before. It represents the mathematical symbol. It's the mathematical symbol for delta, which just simply means change in. So delta T is the change in temperature. So we're going to take whatever the temperature change is for whatever substance we're doing this for, and that's what we're going to plug in there. Change in temperature, change in anything, is always the final minus the initial. So in this case, whatever the final temperature of our substance is minus whatever its initial temperature gives us the temperature change. This is important here because the change in temperature and the Q are going to be directly related in terms of what their sign is, meaning positive or negative. If you're losing heat, what should be happening to your temperature? It should be going down. So if your Q value is negative, then your change in temperature should be negative. And the vice versa is true. A positive Q means your temperature change should be going up. So the most common mistake I see on these problems is right here. So the delta T, especially when that change in temperature is negative. Tendency of some of my students in the past is always to just take the larger number, subtract the smaller number from it. You have to pay attention. Which one of those temperatures is the final temperature? Which one of those is the initial? It's always final minus initial. Real big clue here, real big thing you need to know. Whatever the sign of the Q is, that's what the sign of delta T should be. So if this is negative, this should be negative. If this is positive, this should be positive. Specific heat can never be negative. And M, it's the last one, is mass. It definitely can't be negative. There's no such thing as negative mass. So if Q is negative, that negative sign has to be coming from somewhere, and it has to be coming from the change in temperature, because there's no such thing as negative specific heat, and there's definitely no such thing as negative mass. So these two signs should be directly connected. Whether you're gaining energy or losing energy has a direct effect on your temperature change. And then the last symbol is M. It's mass. So we're going to be probably in grams. Sometimes we'll be in kilograms. You just have to pay attention to what you're being given. And those are 4 variables. So CP, specific heat. Q is the heat energy, the energy being lost or gained. Delta T is your change in temperature. It's final temperature minus the initial temperature. And M is for mass, and that will be in grams, sometimes kilograms. Just have to pay attention to that. Alright, pretty simple equation. This is just a list of general specific heats. These are known, experimentally obtained at this point. We'll reference lists like this relatively often. A lot of these specific heat problems, you'll be given this value and be solving for, mass or change in temperature, change in or energy, one of those things. But reason I bring it up is I want you to always make sure you're paying attention to this up here, because this is important to you in terms of units in your question. This is the most common unit of specific heat that we're going to use. It's joules per grams degrees Celsius. Doesn't mean it's the only one we're going to be using, though, because I could say kilojoules per grams degrees Celsius, or I could say joules per kilograms degrees Celsius. So always pay attention to this and make sure you're in the right units. Most of the time it's joules per grams degrees Celsius. I usually don't mess with this very much, but that also means, like, if I give you the mass of iron or aluminum in kilograms, those kilograms have to be converted to grams before you can do this math, because the unit of mass in this specific heat is in grams. Same thing with joules. If kilojoules has to be converted to joules. Let's look at some of these numbers real quick. Kind of what we'd expect. Water, which we talked about in the last video, it's very high specific heat, 4.18. That's really high, and it's actually really important. Remember, water kind of acts as the temperature control on this planet, because it can absorb so much energy and not have its temperature change very much. As you get down, you'll see water as a solid and water as a vapor is actually, they have different specific heats, which I always thought was pretty interesting, and they're quite a bit lower than water as a liquid. That should tell you that water as a liquid is its most natural and stable state. And then down here you have your good conductors, and look how quickly these specific heats start to drop really fast. The better the conductor, generally speaking, the lower the specific heat. That means it takes very little energy to heat these things up. Gold is a really good conductor. You apply a little bit of energy, it heats up really fast. Metals, generally speaking, have very low specific heats. Alright, well, let's just put this into practice. Let's look at our first practice problem here. So it's 25 grams of aluminum cool from 310 degrees to 337 degrees. How many joules of heat energy are lost? Alright, so let's take this. Alright, so here's our equation. Q is equal to, this one's written in a different order, but it doesn't really matter. Specific heat times mass times delta T. So mass times change in temperature times specific heat. So we're solving for, says how many joules right here, right? How many joules? So that means we're solving for Q. So we should have values for this. What we do, aluminum is on the previous page. Aluminum's down here at 0.897. So I know my specific heat. Oh, whoops. I know my specific heat is 0.897. I'm going to write it in the original. Okay, that's not going to work. Let's switch screens here. Well, first off, let's read this and make sure we. All right, so 25 grams. This is my what? What is that? That's my mass. Okay, so that goes there. My specific heat for aluminum. Specific heat is on the previous page. Here's the important part. Aluminum cools from 310 to 37. This is your initial temperature. It was at 310. This is your final temperature. So it went from 310 degrees Celsius to 37 degrees Celsius. Final minus initial. So we got to keep that in mind when we're figuring out our delta T, because the change in that temperature, the sign of it is very important. Cooling, that's a good indicator that our temperature is going down, which means our delta T should be negative. Alright, so let's flip over to my whiteboard and I'll work this out on my whiteboard. Okay. There it is. Took me a minute. Alright, so I went ahead and wrote down the specific heat for this. So Q is equal to mass times delta T times CP. Alright, so we're looking at practice problem number 1 here. And it says how many joules, so we're solving for Q. It says we have 25 grams, so that's our mass. Change in temperatures, final minus initial. So final temperature would be 37 minus 310. And then our specific heat. Our specific heat for aluminum, I wrote it down up here, is 0.897. 0.897. So when we're solving for Q, really simple. It's just multiplication. I mean, yeah, I have to do that subtraction right there, but other than that, it is multiplication. So let's do that. Real easy. I'm going to do the change in temperature first. So 37 minus 310. I should have a negative number. There it is. Negative 237. I'm sorry, 273. So that's my change in temperature. 25 times negative 273 times 0.897. Alright, now all I have to do is multiply. So times 25 times 0.897. Negative 6,122. Remember, that negative has to be in there. What is that negative telling us? We're solving for Q. Negative Q means energy is being lost. So it has to stay in there. So our Q value is negative 6,122. Now what's the unit? Anybody? 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 It is joules. Q will be in joules. There you go. It's that simple. So that change in temperature from 37, losing that much heat, was at 310, cooled down to 37, meant that it was losing 6,122 joules of energy. Alright. That's not too bad, right? Okay, let's look at practice problem number 2 here. Okay. It says how much heat is given off when 869 gram. Hold on, let me get it a little closer. iron bar cools from 94 to 5 degrees Celsius. Okay, this is pretty much the same exact problem, right? Pretty much the same exact problem here. Alright. So it says how much heat is given off. So when it says heat or energy or anything to do with that, we're talking about Q. So again, we're solving for Q on this one. It says given off, so that implies that energy is being lost. So if energy is being lost, ultimately our Q should be negative. Alright, so it says 8. Let's just fill in the variables that we have. We have our mass is 869 grams. Change in temperature. It says it cools from 94 to 5 degrees. So from means that's our initial. 94 is our initial. 2 would be our final, 5 degrees. So this is going to be final 5 degrees minus the initial, which was 94, which should give us a negative value, and that's good because we already kind of said that our Q should end up being negative here. Times the specific heat, and I wrote it down from the previous page, 0.449. Again, I'm just pulling this number right here from that table that was on our previous slide. So, just like the previous one, it's just a matter of doing some simple math here. 869 times 5 minus 94 is negative 89 times 0.449. And we just do the math now. Real simple here. So 869 times negative 89 times 0.449. And there you go. Negative 34,726. Now this is why we'll sometimes use kilojoules, because when we're talking about a joule, it's really not that much energy. So 1 joule is really not a lot of energy, but you know, something like this not a huge mass of iron, and the temperature change is not extremely large, but it's releasing 34,000 joules of energy. So oftentimes we'll use kilojoules just because the number of joules just gets so big. But in this case, we'll keep it in joules, it's fine. So our Q, negative 34,726 joules. There you go. That's it. Now we won't always be solving for Q. For some reason, every year I deal with people who think you're solving for Q in every single one of these questions. Sometimes you'll be given Q, so just read the question carefully, pay attention to what you're solving for. If it's talking about energy, it's Q. If it's talking about mass, obviously it's M. That should be in grams. Change in temperature, final minus initial, or specific heat. You could be solving for all of those things. So just pay attention to what you're being given and make sure you're plugging the numbers in the right spot. If you're being given Q, pay attention to the wording as well. If it says that that amount of energy was being lost, when that number gets written into your equation, it has to be negative. Or if it says that amount of energy is being gained, again, you got to make sure you're putting that number in with the right sign. So gained energy would be positive. Alright, let's go back to our PowerPoint and we'll finish off this video talking about something called calorimetry, and we'll be done. So come on. There it is. Alright. Last little bit here. Calorimetry. Alright, so the amount of heat absorbed or released during a physical or chemical change can be measured. usually with a known quantity of water in what we call a colorimeter. Um, we'll be doing a colorimetry lab at some point, and we'll have our own colorimeters, and we'll monitor the change of temperature of a process, and we'll end up using the specific heat equation to kind of figure out what's going on. So here's a really fancy one. So this is kind of how a colorimeter should look. Inside the colorimeter, you have an internal container. This is where your reaction or whatever is going to be going to happen. And this one is really fancy. It's got ignition wires if it happen to need extra energy. But this container is inside another container, and that container is surrounded by water. This water is sealed in here, and the temperature of the water is monitored. So this reaction starts happening, whatever it is, this process starts happening in here, and whether it's releasing energy or gaining energy, that energy will basically be monitored by monitoring the temperature of the water. So if the temperature of this water starts going up, so this thermometer's temperature starts going up, what is that telling you is happening here? Well, if the temperature of the water that's surrounding this reaction is going up, that means it's gaining energy. It's getting energy put into it. Well, if it's getting energy put into it, where did it come from? That's right, it came from this reaction. So using a colorimeter, you're monitoring the temperature of the water, which is basically like monitoring the temperature of the surroundings. If that temperature starts to go up, that means this process, whatever it was exothermic. It's releasing energy. Now, if you're monitoring the temperature of the water and the opposite happens, the temperature goes down, that means this process, whatever it is absorbing energy. It's taking energy away from that water. Remember, this thermometer is not monitoring the temperature of the reaction. It's monitoring the temperature of the water. So whatever change in that temperature of the water is, it's reflecting the opposite change here. So the water temperature goes down. That means this reaction, whatever it is absorbing energy from it, taking energy out of it. So this would be an endothermic process. So when you're using a colorimeter, you got to remember that you're not really monitoring the energy of whatever process is the subject of your study. You're monitoring the energy change of the water around that process. So when you're analyzing it later, temperature of the water goes up. That means this was exothermic. That means this process released energy. Temperature of water goes down. That means this was endothermic. It was absorbing energy or taking energy away from the water. Now this is very fancy and it works really well. The whole idea behind this thing is that it needs to be really well insulated so that no energy is lost outside of this box, that the temperature change of this water is 100% a result of what's happening inside the reaction chamber here. Will there still be some energy lost to the outside? Yes, but these things are built really well to kind of like prevent that. Now the ones we'll use in our class aren't nearly as sophisticated, but they work surprisingly well. So what will ours look like? There you go. That's what ours will look like. It's a coffee cup, a couple styrofoam coffee cups, and surprisingly enough, it actually works pretty well. We're going to do one of these at some point. We'll have our own coffee cup colorimeters where we'll have a couple coffee cups. We'll have a process going on inside. We'll monitor the temperature of the water, and whatever happens to the temperature of water will tell us what's happening to that process that we're trying to observe. Really inexpensive materials here, but still pretty effective. Styrofoam is a really, really, really good insulator. It's why it's used in a lot of coolers. Most coolers have some sort of styrofoam on the inner layers because it's a terrible conductor, so which makes it a good insulator. So there's our super, super fancy colorimeter. Now how does this work? Pretty simple. Let's say We have a sample metal that weighs, we added it to 75 grams of water that was originally at 35 degrees Celsius. The final temperature of the metal in the water is 95 degrees Celsius. So they reached thermal equilibrium and the final temperature is 95 degrees. So what happened to the temperature of water? Well, it went up, right? It went up 60 degrees. Well, what does that tell you about the temperature of the metal when we put it in there? It tells you it was really, really hot. This is not a very realistic scenario, by the way. If the metal was that hot, it would vaporize a lot of that water almost instantaneously. Anyways, that's beside the point. So the final temperature of the water and the metal is 95 degrees. So what's happening here? It says A, describe the transfer of heat that occurs in the collimator. Well, this should be pretty straightforward, right? Water was at 35 degrees before the metal was added. We added the metal, they reached thermal equilibrium. Now the temperature of the water is 95 degrees. It went up. So that tells you that the metal transferred heat into the water. The water was heated up by the transfer of energy from the metal to the water. Okay, so it says assuming no heat is lost to the outside, how many joules of energy are transferred? Okay, well, this is pretty simple. We're just we're solving for Q. Using the specific heat equation, solving for Q. So let's do that. All right. So it says, assuming no heat is lost to the outside, how much energy is being transferred? All right. Well, we have all the information we need. We have the mass of water, 75 grams. We have the temperature change of water, which is 35. Initial was 35, final was 95. So 95 minus 35, 60. So it went up 60 degrees. This time it's positive because it went up. And then the specific heat of water is 4.18. So how much energy is transferred? All you got to do is multiply. 75 times 60 times 4.18. And I get 19,562 joules. There you go. Alright. Well, that's going to be it. We'll get a lot more practice with this in the days that follow, but there you go. That's going to wrap up this section of the reactivity unit, and we'll see you when you see you. Later.